Dear students, welcome to the online class. I am Dr. SSC Hiremat. In this video, you are going to study about the Gibbs adsorption isotherm for adsorption in solution. This adsorption isotherm, this adsorption isotherm is applicable to the adsorption in solution. Adsorption in solution means as the adsorption is taking place in the solution, it consists of three components: solvent, solute or adsorbate, and surface area. It consists of three components: solvent, then solute, or this is also called the adsorbate, and surface, that is adsorbent. The adsorbate having lower surface tension compared to surface tension of solvent. It adsorbs on the surface of adsorbent. Thermodynamic interpretation of treatment of the adsorption in solution was studied by Gibbs, and he derived the isotherm known as Gibbs adsorption isotherm. Before adsorption, Gibbs free energy of solvent and solute is given by G equal to N1 mu1 plus n2 mu2. Both this is equation 1, where n1 and n2 are the number of moles of solvent and solute, and mu1 and mu2 are the chemical potentials of solvent and solute. When solvent, solute, that is adsorbate, and surface, that is adsorbent, are mixed, then Gibbs free energy is given by equation G equal to n1 mu1 plus n2 mu2 plus rho into gamma, where rho is surface area and gamma is the surface tension. Suppose this is equation 2. On differentiation of equation 2, we get dg equal to n1 d mu1 d n1 plus n2 d mu2 plus mu2 d n2 plus rho d nu plus nu d rho. Suppose this is equation 3. Thus, by differentiation of equation 2, we get equation 3. We know Gibbs free energy of solution is, Gibbs free energy of a solution is the function of T, P, N1, N2 and rho. That is, G is the function of temperature, pressure, number of moles of solvent, number of moles of solute, and surface area of the adsorbent. Suppose this is equation 4. On partial differentiation of equation 5 with respect to all these variables, we get dg equal to dou g divided by first variable dou t at a constant pressure n1 n2 rho into dt plus dou g divided by dou p at constant temperature n1 n2 and rho into dp plus dou g divided by dou n1 in constant temperature, pressure n2 and rho and dn1 plus dou g divided by dou n2 at constant temperature, pressure n1 and rho dn2 plus dou g divided by dou rho at a constant temperature, pressure n1 n2 and d rho. Suppose this is equation 5, means this g is partially differentiated with all these 5 variables 1 2 3 4 5. Now at constant temperature and pressure first and second terms become zero, and we know partial variation of free energy with respect to the number of moles of component 1 at constant temperature, pressure and n2 rho. This is equal to mu1, that is chemical potential of component 1, and dou g divided by dou n2 at constant temperature, pressure n1 and rho. This is equal to mu2, and another one is dou g divided by dou rho at constant temperature, pressure n1 n2 is nothing but surface tension nu. Then equation 5 becomes in the equation 5 this term is vanished, this is equal to mu1, this is equal to mu2 and this is equal to nu, that is dg is equal to mu1 dN1 plus mu2 dN2 plus nu surface tension nu into d rho. Suppose this is equation 6. Equation 6. From equation 3 minus equation 6, here is at dg, we get dg minus dg is equal to 0, LHS is equal to 0, this equation minus this equation, then mu1 dN1, and these three are removed, then you are going to get N1 d mu1 plus N2 d mu2 plus rho into d nu. Suppose this is equation 7. Equation 6, equation 3 minus equation 6, we are going to get this is equal to 0. Before adsorption, when solute and solvent are pure, then we know N1 naught d mu 1 plus N2 naught d mu 2 is equal to 0. Suppose this is equation 8. On rearranging this equation, we get d mu 1 equal to N2 naught d mu 2 minus divided by N1 0. Suppose this is equation 9. Now, by substituting d mu 1 from equation 9 into the equation 7, we get equation 7 is equal to, that is 0, N1 as it is, and mu1 equal to minus N2 d mu2 divided by N1 naught, and this is N2 naught, N1 naught N2 naught plus N2 d mu2 plus rho into du nu. Then taking mu2 as common, we will write N2 minus this becomes minus N1 N2 naught divided by N1 naught into d mu2 plus rho d nu. Then on rearranging, this is 0, N2 minus N1 N2 naught divided by N1 naught, divide the both side of this equation by rho. We are going to get d mu2 plus d nu. By substituting N2 minus N1 N2 naught divided by N1 naught divided by rho is equal to tau. Where tau is the excess surface energy, is the excess concentration of the solute per unit area. Of the surface. This is called the tau. Then that is equation 9, and we may write this equation as 10. Equation 10 becomes tau d mu2 plus d nu is equal to 0, or tau is equal to minus d nu divided by d mu2. Suppose this is equation 11. And here this is N2 minus N1. This is the excess concentration of the solute, means 2. This is for solute 2. Therefore, tau is 2, means for the excess concentration of the solute. We know chemical potential of solute is given by knowing activity of the solute by equation mu2 equal to mu2 naught plus RT ln A2. where A2 is activity of solute. On differentiation, this is equation 10. On differentiation, of equation 12, we get d mu2 equal to mu2 naught is constant, becomes 0. Then we will get RT d ln A2, so which is equal to RT d A2 divided by A2 divided by A2. By substituting this, thing d mu2 in equation 11 and taking activity A2 equal to concentration C2 of solute by τ2 equal to minus d mu divided by d mu2 equal to RT d C2 divided by C2, that is T2 is equal to minus C2 divided by RT d nu divided by dC2. Suppose this is equation 14. Here C2 is the concentration of the solute, R gas constant, T is temperature, d nu is the surface tension change, and dC2 is the change in concentration of the solute, and the change in concentration of the solute at the surface is given by τ2, this at constant temperature. And this becomes T, this also becomes T, and this also becomes T. This is at a constant temperature. Equation 14 is known as Gibbs adsorption isotherm.